Hello students, 2022 electronics essay question. We are in that. First diagram we are getting. Yes, you can see here we have a transistor, of course, and here we have a Zener diode, and we have two resistors. Students, I actually hope you have done questions from these. Now we are 2022 question. So you must have done other past paper questions. We actually did 2022 and 2023 past paper essay question from electronics, right? So now we are 2022 questions. If students, if you are just getting into the question, then if you have done questions, I mean, if you have practiced this series, the question is really easy, right? So if you haven't, yes, of course, it's really difficult, right? That's how it's very simple. Right, let's dive into the question now. So first, I'm suggesting students, you have to try, if you are practicing this for an exam, right? So you have to try this question first and then go through with this video explanation. Remember students, there are plenty of sources. You can find the answers for these past paper questions. But here students, I am actually guiding you through the things you must have studied when doing this question. Something like that, right? So you will always get something out of this video series for sure, right? So grab a notebook with you, so with a pen as well. So write down the important theories that I'm telling you, right? Maybe certain theories that I'm telling you may not be important to you. You may know it. Some maybe it's a small tiny bit of theories, but still it might be really helpful for you. So write them down, right? Let's get in now. First question. Let's read it. The circuit shown in figure 1, this is the figure 1, is used to obtain an appropriate output voltage Vout. This is the Vout voltage from a variable input voltage Vin using a Zener diode. This is the Zener diode and a transistor arrangement. The circuit uses a Zener diode with minimum current 10 milliampere. So minimum current that can go through this is 10 milliamperes. A silicon transistor. Okay. Right, silicon transistor means VB, this is B, this is collector and this is emitter. The potential difference across base and emitter is 0.70. That's what they meant by silicon transistor. Right, RL 90 ohms given and Zener diode 8.3, potential difference of P23. Right, so first question, calculate the following. Vout. Let's look at the question now. We have a Zener diode here. Students, Zener diode is a diode which in most cases actually operates in reverse bias form, and it can control the potential difference across its terminal. So here, when it's in reverse bias, it will maintain a constant potential drop of 8.3 between its terminals. So that's the ability of the Zener diode, right? So Vout is the potential here. Potential here it's 0. So potential difference 0 and Vout. This is Vout. So you can see, so Vout is the potential here. So potential here, it's connected by a wire. Of course you can see the potential. That's same, right? Here potential, here V, here also V. The same potential. Vout, same Vout potential we can see. Right. Here we get 23 volt. Right. Now students, only because of this resistor, there's a potential difference between this Vout and V. Right. I'm planning to, we don't know the actually current through this, so we cannot find the potential difference across this and then we can subtract it 23. We can find Vout, but that's not the method. The only potential, other potential we know is this 0 volt. And potential here is 0 as well. Then the potential, if the transistor is forward bias, then the potential at this point should be 0.7. And this Zener diode is maintaining 8.3 potential difference across its terminal. So one terminal is 0.7. So the other terminal, it has to be, that's Vout, right? So Vout, I hope you can see this. Vout minus 8.3 is equal to 0.7, then Vout is equal to 8.3 plus 0.7, that's 9 volt. That's how you get the answer. That's the answer for first question. V out, take VB 0.7. We have done that question. Students, you have to know these theories to get the question. So it's not that hard. But students, remember that you have to practice your theories. If you haven't practiced your theories, you don't know these stuff. That you have to take voltage from this end and it should go that end. So it will be automatically being practiced inside you while you do questions. So you have to do electronics MCQ questions, small essay questions, and many more. Let's get into the second part of the question now. Right. Second part, current IL. That's actually a current electricity question. See here the potential you have found out. That's 9 volt. Right. And the potential difference is 9 volt. So simply what you have to do is you have to apply V equals IR across this RL resistor. So V is 9, IL 90. So IL equals 9 divided by simply 90. So it's 1 over 10, 0.1 amperes. So current through here is 0.1 amperes. Easy question. Right. Third part, current IS. What's IS? This one. Again, because IR. Simple language. Here it's 9 volt. Here it's 23 volt. So apply V equals IR. For this resistor, we can find IS. Right. What's the value? IS, RS. It's 70 ohms. 70 ohms. Let's do the simplification here. Right. I hope you can see it here. So potential difference across this resistor is 23 minus 9. So that's 14, right? Yeah, 14. So let's apply V equals IR for this resistor. 14 equals IS into R 70. So IS equals 14 over 70, right? So it's 2 over 10, 0.2 amperes. Students, from here we get, from input we are getting 0.2 amperes, and here we get 0.1 amperes that is going through RL. Fourth part, IC corresponding to the minimum Zener current. Say now here we have minimum Zener current. So what's the IC value? This is actually Kirchhoff question. Say now, look at it. Here in the circuit we get 0.2 amperes current up to here from the input. And at this point, certain amount of current will go through this, and certain amount of current will go through this, certain amount of current will go through this. So it will get divided into 3 parts, 0.2 amperes. Now at the beginning of the question we have found it's 0.1 ampere for this part. Right. This is IC, that is what they are looking for. And here this value, the minimum Zener current is 0. What's the value? That's 10 milliamperes, right? 10 milliamperes. 10 milliamperes in amperes. 10 milliamperes. What's the value? So here we get 0.1 amperes. That means you can do it actually in milliamperes. That's easier, right? So here 0.2 amperes mean multiplied by 100 we get 200 milliamperes. So here we get 100 milliamperes through this 10 milliamperes. So let's write the equation here again. Students, remember that current electricity theories and electronics theories go hand in hand, right? So you should know these for better. 200 milliamperes should be equal to IC plus IZ plus IL. IZ we know, no IZ, that's 10 milliamperes, and IL 100 milliamperes. So 200 minus 110, so we get 90 milliamperes. So IC will be 90 milliamperes. That's the answer they are looking for. Right. We have done first part. Right. The first part, part B. Right. Here in this question, calculate the amount of power dissipated across RS This one when V in equals 23 volts and 30 volt. Right. So when this is 30 volt and 23 volt. One thing, students, you should remember. This 0.7 volt, that won't change. And of course, this 8.3, it's a voltage regulator. So the potential difference across the Zener diode, it won't change. It will be at 8.3. Right. The purpose of using it is to regulate the potential difference across it. So it will regulate the potential difference across it. So here the potential is 0.7, 8.3, here it's 9. So this Zener diode and the transistor both together, it will make sure the potential at this point will be held at 9 volt as far as the input voltage that is greater than 9. So if it goes down to 8, yes, the circuit will not operate properly, that is for sure. But until as far as it is greater than 9 volt, this circuit will make sure the potential at this point and all the output voltage will be at 9 volt. That's the purpose of using this circuit anyway. Right. Now we need to find the power dissipation at this. So again, that is also current electricity equation, right? Of course, power equals V squared over, that's the equation, I'm going to use it here. But there are two other equations, I squared R and IV. Right? You can apply that equation as well. So in the first case, when the output is 23, here it's 9, so the difference will be 40. So here the potential difference, I'm going to apply 14 squared divided by 70, right? 14 into 14 divided by 70. So that there goes 2, 10, 28 divided by 10, it's 2.8 volt. It's volt, right? Power, 2.8 volt. So when it's 30, the potential difference will be 30 minus 9, that's 20, 21. So 21 into 21, actually they have given this question, it's really easy to simplify, right? In that format, divide by 70. So 3, we get 10, so 63 divided by 6.3 volt. Easy question. In the second part, so calculating 1 and 2, you may get 2 marks, maybe 1 marks even. Using calculations in B1, briefly explain how a change in the input voltage is regulated by the circuit. That's a good question. Input voltage will be regulated by this circuit for sure. I have actually explained it to you earlier. If we make sure the potential difference here is 0.7 and here it's 8.3, that's it will make sure 9. So the additional power from this 30 volt is gonna dissipate here. See, when the potential is 23 volt, it dissipated the RS resistor, power dissipation at RS resistor was 2.8. But when it's 30 volt, it is increased to up to 6.3 volt. So the transistor and the Zener diode will maintain the potential at 9. So when the input is increased, the power dissipation at the RS resistor will be increased. So additional power, additional voltage will be consumed by this RS resistor, basically as heat, right? That's what you have to write. Briefly explain. Students, you have to go through answer marking schemes for sure for these. Remember that when you are studying essay papers, students, the key, it's a golden rule actually, you have to go through the markings. So take a marking scheme and go through it and see the way they have given the answers or the keywords they are looking for. Right. So we have done part B. Right. There's another part, I guess, for this is part C. The circuit in figure can also regulate the voltage variation in V out, okay, due to an increase in output load resistance. This, what happens? The load resistance is increased. Let's see. If a load resistance is increased, okay, increased, what will happen to Zener current, IZ and IC? Explain your answer. Right. So this actually you can explain by giving simple logic, right? Say now, if this resistor is increased, you have to write down the connection between these. Let's write down the connections here. If only, right, now the argument must be inside your head, but there must be a way to write it down, right? Even I had, when I was doing my A-levels, I had this problem, like I know what's actually happened, but I don't know how to write it. So basic method to express everything is writing an equation. It will express so many things. So input current, say I in, is equal to IZ plus IC plus I. So when RL is increased, IL will decrease. Right. That argument you have to write. Right. The first part B. Briefly explain how the Zener diode and transistor combination regulate the output voltage when the load resistor is increased. Right. So when RL increases, we know that IL will decrease and IC will increase. Right. Then the output voltage, so when this one goes down actually, by any means, if this voltage is increased, then the current IS will be increased. If the current IS is increased, the potential difference across this one will be different, right? So because of that, the potential drop at this point might vary. But remember students, the Zener diode and transistor will not allow it to happen. What basically happens is, when IS current increases, automatically increases or something, this one will make sure that current will go through the Zener diode by maintaining 8.3 volts. That's the ability of the Zener diode. So the Zener diode itself will, the highest, when IC increases, that will go through the transistor. So there won't be any change because of this IC, right? Even if IC is increased, that will go through the transistor, so it won't make any changes to this 9 volt potential here. Whereas in IS, in any case, if IS is increased, the additional current will be sent through this Zener diode. So with this Zener diode and transistor, with this combination, it will make sure the potential V out is constant, right? So that of course you have to write. So just go through the video, just go through with the marking schemes. You will see how it's properly written there. So that of course you have to write. Students, remember, you have to practice writing essay questions compared with MCQ questions. MCQ questions is a different thing, essay is a different thing, right? So here you have to write the arguments. So you have to practice writing arguments for sure, right? If you have analyzed actually essay questions, now students, you must have seen that we have to write so many arguments. What if this is like this and then something like this will happen? So you have to explain quite a lot. Remember that. Moving into next part. Right, students, we are in the last part C, right? Yeah. Here we have an operational amplifier. Maybe an operational amplifier, maybe not. They're asking that question even in the question, right? And we have a junction transistor. Yes, we have a Zener diode here as well. So it's combined question, right? So students, some years actually we are expecting we will be getting a transistor question, we will be getting operational amplifier question, Zener diode question, gates question and all this. But here in this year 2022, actually we have a combination. Only thing that is missing is we don't have a gate question here in this year, but in most years actually we'll be getting a gate question, so please be ready for that for sure. But in this year actually we might be having a good gates question in MCQs, maybe. Let's see for that. Right, getting into this question, you have to have basic understanding of electronics devices for sure. Right, first question. Write down the operational mode of operational amplifier in the above circuit for the given choice: inverting amplifier, non-inverting amplifier and comparator. This is the non-inverting input and this is the inverting input. Right, students, there are two methods to bias an operational amplifier, open loop and closed loop method. Here basically there's no direct connection between output and input. No direct connection. Right? There's no feedback or anything like that. So it's open loop. Basically in open loop methods, students actually we are using to check whether this positive voltage is greater than negative or not, something like that. If there's a small potential difference between these two terminals, it will be increased by 10 to the power 5, very high value, and we get the output value. So if the difference is negative, we get the negative high output. If the difference is positive, we get positive high output. So from that we can find out which one is greater. Compare. So it's a comparative. You don't have to write all these things, just it's a comparative. Right, next question. Under bright sunlight, we get good sunlight. R2 is adjusted to produce 14 volt output voltage. Here 14 volt output voltage. When R1 equals 9 kilo ohms, here 9 kilo ohms, and R2, actually we can vary that value, but here they have given it's 5 kilo ohms. Here it's 5 kilo ohms. And here student it's 14 volt, right? 14, 14, 14, 14, one line, right? The same concept we used earlier. Calculate the most appropriate maximum for VZ. For the Zener output VZ1 we have. Right? Now our purpose is to get here 14 volt. The transistor here, it has to be a positive value. Then only this will be forward bias and we get a potential 14 here. Right? The circuit will work once this is forward bias in active region or saturated region. So for that, the potential here it has to be positive. From that we have to start. So this output here, we out from the operation amplifier must be a positive value. So here the non-inverting input potential should be greater than inverting input potential. Right? So with the given value they have given, by using the given value, we can find the potential at the positive terminal. Let's find the potential at the positive terminal. Students, when you are doing this question, then actually you can use voltage divider method. So just basically write using the voltage divider method, finding the potential at positive terminal. So the ratio we have to R1 is to R2 ratio we need to consider. So R1 plus R2 R2 divided by R plus R2. That's the fraction. So we multiply that fraction by 14 volt, we get V positive value. So R2 5, R1 9 plus 5 into 14, easily simplified. 14 it's 5 volt. Right, now we know the potential here, it's 5 volt. Students, the potential here, if it's 4.99, the potential difference will be 0.01. The output potential will be a positive value. If it's 4.999, still there's a small positive potential difference. Here it will be positive value. So they're asking what's the maximum value we can get here. If it's more than 5, the potential difference here, if it's more than 5 by any chance, because here it's 5, permanent, it's a fixed value, it's 5. If it's 5.1 here, this potential will be negative. So it won't operate properly the circuit. So for the circuit to operate properly, the negative terminal must be smaller than the positive terminal. So maximum value VZ can go 4.999, something like that. We cannot write something like that, right? So we can go up to 5. Students, if you have done past paper question, you must have come across certain situation like this. So then you know, right? Right. It's not 4.9. I can write it at 5. So that's here. This important thing is here, student, doing past papers. When you get the experience by doing questions, you know how to put the answer. You may have the skill to do the calculations and everything, but you are not experienced. If you are not experienced with writing the answers, you are in trouble, right? So here the maximum value this one can get is 5. Knowing, alright, do the calculation and write down the maximum potential here can be 5 volts. So VZ is 5 volt. Output of operation amplifier saturate for 100 microvolt potential difference. Here, the small difference as I mentioned earlier, it's 100 microvolts, small difference. The output will be, when the output voltage of the circuit is 14 volt. Here is 14. Assume that the output saturation voltage of the operation amplifier is 2 volt below the supply voltage. 2 volt below the supply voltage, that's 14. It's 12 volt. So here we have 12 volt, here input 100 microvolt. So they're asking us to find operation and open loop gain, right? Yeah. So capital A open loop gain equals V out divided by V1 minus V2. What's V1 minus? V positive minus V negative. Right. So V out 12, V positive minus V negative, 100 microvolt, 100 into 10 to the power minus 6. So 10 to the power minus 4, that goes off. 12 into 10 to the power 4. That's the open loop gain. Right. Easy question. Fourth part. Briefly explain the action of operational amplifier and the transistor in this circuit when the solar panel produces less than 14 volt under weak sunlight. If here the voltage is 14, let's see what's happening. If it's below 14, that means the potential difference across this R2 will be lower than 5. If this is lower than 5, now we know that this one will make sure the potential at the negative terminal will be 5. Sure. So this one, this will be slightly lower than the potential at this point. The output will be negative. The transistor, there will be no IB current. The transistor is in cutoff region. These things you have to write. Key points. So this will not operate properly. So what will happen? The V out voltage will be easily equal to the potential given out by the solar panel or solar input voltage. So the potential will not be maintained at 14. It will vary with the potential at the solar panel. Right? That of course you have to write the key point, the cutoff of the transistor. The output will be negative. IB will not be IB or some stuff like that. So as I'm telling you again, go through the marking schemes and all that. Try to understand the method. They have written the answers, right? And practice questions. Students, remember that. Maybe you may not have time to do massive or big questions, big, large, huge questions. Yes, sure that I'm using all the words for being huge, right? So what you have to do is find small questions. Small questions. That's with operation amplifiers. That's with transistors and all that. Then you have the practice. Then come the combined questions, because you have to do combined questions, because as an essay question you have to face combined questions for sure. So practice is the key thing here, students. You don't have to fight that much of effort actually, whereas you are going to apply in mechanics question, properties of matter question, or even optics question, in heat questions. You have to put lots of effort. But here the practice is the only thing. You don't have to be that smart to do this kind of question, right? So we have done 2024 questions, 23 questions, and it's 22 questions. I'm going in this way. Anyway, so I'm inviting you students just to try lots of questions as far as possible. You have to find out what are the questions you're going to do at A-levels. In our A-levels, we get 4 essays to do. So find out what are the 4 essays that you are going to do. For that, you have to practice questions and find out which are the best 4. Good luck.